Hello APC Mechanics students in Unit 4 System of Particles and Linear Momentum Class 6 4.3 Conservation of Linear Momentum Collisions Part 2. Exercise 1. For an impulse momentum experiment, students collect data on a collision between blocks A and B. A force probe attached to block A is used to measure the force exerted by block A on block B as a function of time during the collision. So basically this is block A and that's block B. So this is A, that's B. And here we have a force probe. Whenever the force probe is attached to A, so they're telling us the data collected shows a positive force that is used to determine the impulse on block B. Whenever the force probe is attached to A, then we're gonna measure the impulse exerted by A on B. The force sensor is removed from block A and attached to block B. So now we remove the force probe from A and we connect it to B, and the experiment is run again. Which of the following correctly describes how this affects the data and if this impulse on block B can still be determined? So if you pay attention to the question, they're telling us if the impulse on block B can be still determined, which is this one. The data can only be used to determine the impulse on block A and not block B. This is wrong. Now here we're gonna measure the impulse on block A, but remember that impulse on block A would be equal to the impulse on block B. The data can only be used to determine the impulse on block B, not block A. This is wrong because we know that both are equal. The data cannot be used to determine the impulse on block A or block B. That's wrong. The data can be used to determine the impulse on block B and block A. That's true, because by this we're gonna measure the impulse exerted on. So initially, if we're measuring the impulse on block B, then this would be on block A, which is equal to the block B. Exercise 2. In an experiment, students use motion sensors to measure the speed of objects 1 and 2 of masses m1 and m2 respectively that collide head-on while moving along a smooth horizontal surface. Consider velocity to the right to be positive. All motion is along a straight line. The speeds of object 1 are v1i before collision and v1f after the collision. The speeds of object 2 are v2i before the collision and v2f after the collision. Before the collisions, object 1 is moving to the right and object 2 is moving to the left. Both objects reverse their direction of motion during the collision as shown. Which of the following expressions can be used to determine the magnitude of the impulse on object 1? We know that the impulse, the magnitude, would be equal to delta p1, which is equal to delta p2 in magnitude, which is m1 delta v1, and that would be equal to m2 delta v2. But remember that delta v is the change in velocity and not in speeds, which makes A to be the correct answer because there is an additional minus sign due to change in direction. Now that's wrong, because this should be plus. Moreover, 2 cannot be combined by 1. Both should carry the same indices, which either 2 or either 1. In an experiment, students use motion sensors to measure the speed of objects 1 and 2 of masses m1 and m2 respectively that collide head-on while moving along a smooth horizontal surface. Consider velocity to the right to be positive. All motion is along a straight line. The speeds of object 1 are v1i before the collision and v1f after the collision. The speeds of object 2 are v2i before the collision and v2f after the collision. Before the collisions, object 1 is moving to the right and object 2 is moving to the left. Both objects reverse their direction of motion during the collision as shown. After analyzing the data, a student noticed that the motion sensor measuring the velocity of object 2 was not facing directly along the line of motion of object 2, but was angled slightly. How would this affect the data collected by the student? Now, if the motion sensor is placed here and it's measuring velocity along this line of sight, now if you project this along the line of sight, let me make it more apparent. Let me say the motion sensor is here. Now notice that if you project this vector, which is the velocity, along this line of sight, you would notice that this is smaller, because if you have vector initially like that and you want to project it along a certain horizon or a line of sight, you will notice that the projection would be always smaller. So whenever you project a vector, you expect that the projection is smaller. So we're measuring the projection of the velocity and not the velocity itself, which makes the actual speeds of object 2 are smaller in magnitude both after and before the collision. So the speed that we're measuring before the collision and the speed that we're measuring after the collision, in both cases, is smaller than what we expect. Identical net forces act for the same length of time on two different spherical masses. Same force, same time, means that the change in the linear momentum is the same due to the impulse. Okay? Now, two balls A and B have the same mass and diameter but are made from different types of rubber. The balls are dropped from the same height above the floor. After colliding with the floor, ball A bounces higher than ball B bounces. Which of the following quantities must necessarily be larger for ball A than for ball B, which is the impulse basically, the impulse exerted by the floor. The average force alone, it's not enough. The amount of time alone, it's not enough. Both of them gives us the impulse, alright? The momentum just before colliding with the floor, if they have the same mass and they have dropped from the same height, then they have the same momentum, which means this is wrong, and the same kinetic energy, which means this is wrong, before collision. Exercise 6. Object A has a mass of capital M and is moving in the positive x direction. It collides with object B, which has a mass of 2m and is initially at rest. So before collision and after, the object A has a mass of capital M and it's moving in the positive direction. It collides with an object B that has a mass 2m and the velocity is 0. After the collision, object B has a final velocity of v in the positive direction. Which of the following best describes the impulse object B exerts on object A? Now the impulse can be determined by two methods, either from, so we can determine the variation of momentum for object A, which is equal in magnitude to the variation of the momentum for object B. So the impulse is either this or this one. Now we only have information about B. So B in this case, delta P of B would be 2m multiplied by the final velocity minus the initial velocity. The initial velocity is 0. That would be 2m multiplied by v. And here they're asking us the impulse object B exerts on object A. We need to pay attention because the impulse is a vector quantity. Now, due to interaction, so impulse would have the same direction of the force exerted by B on A, which is to the left, then we need to choose A. In magnitude, they are both equal to 2mv, but at the end, this is a vector quantity. They're asking for the impulse of object B exerted on A, which is to the left. Exercise 7. A ball of mass m is dropped from rest at a height h and collides elastically with the floor, rebounding to its original height. What is the magnitude of the net impulse on the ball during the collision with the floor? So this is before, and that would be after. That's the floor. So the ball has been dropped from a height h and it's about to hit the floor. Then if this is the height h, then its speed momentarily before it hits the ground is given by v is radical to gh. Now because the type of collision is elastic and the ball will rebound to its initial height, then momentarily after collision we expect that the speed should be also v is radical to gh, because according to conservation of energy, if the ball has to reach again its initial height, then its speed before collision should be v is radical to gh. Then delta p in this case, which is the magnitude of the net impulse j, that would be m delta v, but here this is the change of velocity, which is m into radical to gh plus radical to gh, and that would be the double of m multiplied by radical to gh. But notice that it's none of the answers. Now 2 If you insert 2 inside the radical, that would be 4. 4 multiplied by 2, that would be 8. So it's given by m radical 8gh, which makes E to be the correct answer. Exercise 8. Suppose you wish to qualitatively test the validity of the impulse momentum theorem by rolling various balls along a table toward a wood block. So this is the table. That's the rolling ball. And that's the block. When each ball reaches the block, it pushes the wood block forward and the ball bounces backward away from the block. Which of the following describes the best procedure for the experiment and a correct interpretation of possible results? Use the ball of the same mass and the same initial speed but different amount of elasticity. This is wrong, because whenever we're talking about the theorem, and the theorem is the impulse momentum theorem, has nothing to do with the elasticity. It's about J being delta P, which is m delta V, and in magnitude for an isolated system is assumed to be constant. So it's all about when m is high, delta V is low, when delta V is high, m is low. Use balls of different masses but with the same amount of elasticity and the same initial speed, and repeat this procedure for each ball. They're telling us when smaller the mass balls, so if a smaller mass balls causes more movement of the block, this is consistent with the prediction of the theorem. Now, the motion of the block depends on the impulse that is being exerted on the block. Now, we say that m is high, delta V is low, and delta V is high and m is low whenever we're talking about the same object. But whenever we're comparing two objects, we need to take J into consideration. If the masses are small, then all of this quantity is small, which means that the impulse exerted by the rolling ball on the block is small. Then we don't expect that the ball will cause more motion to the block. So this is wrong. Now, as for part C, they're telling us use identical balls with the same initial speed but blocks of different masses and repeat the same procedure for each block. If the ball rebounds with more speed when it pushes a large block than when it pushes a smaller block. So basically they're comparing now the both objects. So let me say that m1 delta v1 equals m2 delta v2. If the ball rebounds with more speed when it pushes a large block, so they're saying that if delta v1 increases, this means that due to a larger block, which means that m2 should be greater, and this is reasonable compared to a smaller block, then this is consistent with the prediction of the theorem. So let's keep that as an option, and let's see if we can eliminate D and E to make sure that C is correct. Use balls with different masses but with the same amount of elasticity and same initial speed, and repeat this procedure for each ball. If the balls that rebound with more speed cause less movement of the block, so let me say m1 delta v1 equals to m2 delta v2. So they're saying that rebound with more speed, which means delta v is greater. This means delta v2 should be wrong. No, because they are directly proportional. If this increased, then this should increase, but it's decreasing, so that's wrong. Use balls of the same mass and with the same amount of elasticity, but roll them toward the block at different speeds and repeat this procedure for each speed. If the balls traveling at higher speed cause less movement of the block, so let me write again m1 delta v1 equals to m2 delta v2. They're saying that if the balls traveling at higher speed, so delta v1, so in general the momentum is greater. So here no need even to use this interpretation, because we know that higher speed, which means higher momentum, cause less movement of the block. No, because we know that whenever the momentum is high, this will cause the block to move more. This is consistent with the prediction of the theorem. No, that's wrong, which makes C to be the correct answer. So let me just write it down. Okay, that's C. Now exercise 9, two pucks A and B with unequal masses slide with equal speeds. in opposite directions on a horizontal surface with negligible friction as shown in figure 1, the pucks undergo a head-on collision. After the collision, both pucks move to the right. The speed of puck A has decreased, so VA will decrease. And the speed of puck B will increase as shown in figure 2. Which of the following is a plausible explanation for the observed behavior of the pucks? The magnitude of the change in momentum is the same. So basically we will limit ourselves to A, B, and C, because here in D and E they're saying that the magnitude of the change of momentum is greater or less, and this is wrong because we know that the change in momentum would be the same due to the impulse momentum theorem. Now the magnitude of change in momentum is the same for each puck, but puck A has more momentum initially. That's wrong. Yes, that's true because the speed has decreased, so A is the correct answer. Now let's check B and C. The magnitude of change in momentum is the same for each puck, but puck B has more momentum initially. No, because we know that the momentum of B has increased due to the increase in speed, so that's wrong. The magnitude of change of momentum is the same for each puck because each puck has the same momentum initially. No, we know that separately each momentum is different, but the total momentum remains the same, which makes A to be the correct answer. Now finally, exercise 10, which is an exit ticket for today's video. Object A of mass capital M is moving east at a speed V. The motion of the objects, it collides with object B of mass 2m that was initially at rest. The motion of the objects before and after the collision is along the same line. After collision, object A, so that's before, and after, object A is moving west with the speed V over 3, so that's the mass m, and that's speed V over 3. What is the speed of the object B? So the mass would be the same, and we're searching for V. This can be done using conservation of momentum. If this is a free response problem, we say that the system is isolated, then the linear momentum is conserved, then P initial would be equal to P final. Now object A has a mass m multiplied by positive speed V to the right, plus 0, because this is initially at rest, mass m multiplied by speed minus V over 3, which represents the velocity, plus mass 2m, and we're interested in finding the velocity V. Now m with m with m, that would be cancelled. That would be V equals minus V over 3 plus the double of V, and we're interested in searching for this velocity V. Let me say this is V prime in order not to confuse. Now 2V prime would be V plus V over 3, which is 4V over 3, which means that V prime would be 4V over 3 divided by 2. So let me say here it's divided by 2, because we take 2 down, and that would be 2V over 3, which makes C to be the correct answer. Then thank you for watching, and see you soon in a new one.